Okay, ladies and gentlemen, here we go. Regroup. 5.4, slope as a rate of change. So we've already learned about slope. Remember, slope is represented by the letter M, and it's calculated by finding the rise over the run of any graph. We can also do it just using points, but you'll find that out a little bit later. But today we're going to learn that slope actually corresponds to a rate of change. Now, have you ever heard those words before? Rate of change.
Change of rate, yeah.
You said it like yesterday.
So your rate of change is, well, let's draw a little diagram. You have a little bit of space at the top, yeah? About that big of a space, okay? I want you to use this side right now, okay? So I'm going to just draw a little graph. Basically, if we have, note that's your example 1. If you have a time distance graph, so where time is the independent variable and distance is the dependent variable, and you have a person or a car or a cheetah or whatever, and it's traveling at a constant rate, then over time it will cover more distance. Right?
If it slows down.
Over more time, it will cover greater distance if it's going at a constant rate. Now, what word do we use to describe something that's traveling at a certain rate?
Fixed amount.
Speed. Okay? Speed. So really, this line represents the car's speed. Or the cheetah's speed, sure. So if we calculate the distance that it goes in a certain amount of time, we will actually have been calculating its speed. Now let's look at our equation again for slope. Slope is rise over run. Look, distance is the rise, time is the run, and it equals speed. So the slope is related to a rate of change.
Is that all the time?
That is all the time.
Why can't
Okay?
we just keep that
Okay.
rise of the run?
In the rest of your space in the top right, you can put this definition. Rate of change. And that is a change in one quantity relative to the change in another quantity. The change in one quantity relative to the change in another quantity. Well, what does that mean? That means exactly what our little graph on the right says. As time changes, distance will change. Sometimes distance might change slowly relative to time. Sometimes distance might change quickly relative to time, right? Driving in the city might look like this one. Driving on the highway might look like this one. Okay? Does that make sense? And you can see how one has a steeper
Rise.
slope. Okay? Slope is the measure of the
I
steepness.
try so hard.
Okay? Good. So there's your definition. Let's keep that in mind as we move into our first example, which talks about speed. So we've got Sarah. Sarah runs every morning before school.
Why?
Dedication. One day, she ran 5 kilometers in 20 minutes, which is quite quick, actually. 5 kilometers in 20 minutes. We need to calculate the rate of change of Sarah's distance from her starting point, okay? So here we go. We're going to put a couple notes here. We said that the rate of change is the change in one quantity relative to the change in another quantity. So in this scenario, what are the two quantities?
Distance and time.
Time and distance. And which one changes relative to the other one?
Distance changes to time.
Distance changes relative to time. Okay? So here we go.
Time doesn't ever change.
The rate of change. The rate of change is the distance
Oh, there's your graph there.
traveled relative to the time elapsed, comma, expressed as a fraction. Okay, what does that mean? That means we have rate of change equals the change in distance divided by the change in time. And I hope your mind is already kind of going back to those graphs and thinking about slope and thinking about rise over run. So let's say we are traveling like this. Then our change in distance is our vertical change, which is our rise, and our change in time is our horizontal change, which is our run. Okay? So let's plug in what we know. We know the change in distance. How far is she running this morning?
5 kilometers.
5 kilometers. Let's put a 5. And the change in time? 20 minutes. That equals 0.25. So you could get your calculator out, you punch in 5 divided by 20. What does that tell us?
Well, you see, every 0.25 seconds, she is
Every 4 minutes she is going 1 kilometer.
Hold on. Our rate of change has to do with the distance with respect to time. We divided...
Oh, I just have to prove you wrong.
Guys, so this answers your question as well. We have 5 kilometers, and we divided by 20 minutes. So that means we've gotten 0.25 something per something.
Kilometers per minute.
Kilometers per minute. Okay, this is measured in kilometers per minute. So she goes a quarter of a kilometer each minute. So yes, it takes her 4 minutes to do a kilometer, but we did not do how many minutes will it take her to do a kilometer. That would look like this.
you just flip it.
Okay, but that's not what the question is asking. We're getting a rate of the distance relative to the time, which is 0.25 kilometers per minute. Okay? Good. B. B says to graph Sarah's distance as it relates to time. So, on your graph, you can draw your axes, 2 blocks in from the left, 2 blocks up from the bottom,
What is 2 blocks?
so that you have space to write your numbers and it's nice and neat and clean. Okay? And go ahead and add your labels to your vertical and horizontal axes. Tell us what they're measured in. Time is measured in minutes, and distance is measured in kilometers. And the distance, we really only need to get up to 5. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And time, we need to get up to 20. So I'm just going to put a 20 out here and split it in half and call that 10. And I could split it in half again and call that 15. And that 5. And now the only points that I know for sure, because I don't have a table of values here, the only points that I know for sure, and there's 2 ways to think about this, but I'll show you the easiest way first. The only thing I know for sure is that after 0 minutes, she's gone 0 kilometers.
Good observation.
Okay? So I know that's her starting point.
Or the,
Yeah, at 0, 0, the origin.
okay, source.
And I know that after 20 minutes, she'll have gone 5 kilometers. So I know this point is on my line. I know she's traveling at a constant rate. Okay? And all I need to draw a line is 2 points. So this is sufficient.
What?
That's,
The vastus los.
what would that be?
Okay?
Yes, it does.
I mean, you can just add points on your line.
You don't even need to add points on your line. If I said, okay, tomorrow she runs the same rate, but she only runs for 10 minutes, how far will she run?
Half the distance.
You just say, okay, at 10 minutes, she's right here. at 2.5. Okay? If I said, okay, she's going to run 15 minutes the next day, you just go up from there, and you come across. It's in there somewhere. Okay? Or I could ask the opposite question. I could say, okay, she's actually going to run 2 kilometers. How fast could she do it in if she did the same rate? Then she would do this. Okay, she'd do that in about 7.5 or 8 minutes. Yeah?
That's really fast. She's a fast.
Does that make sense? That's your graph right there. Done. Okay? Time on the horizontal axis, distance on the vertical axis, 0 to 25. Plot it, draw a line. Okay? The other way that you could draw this, I'm just going to erase this for a second. The other way that you could draw this is you could say, okay, she starts at 0. I know that. And how far is it going to rise every minute? 0.25. So I could go over 1 minute, up 0.25. 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 I could do that the whole way. Or I could say, oh, this reduces. I could say, okay, this reduces to 1 over 4. I could go up 1 over 4. 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 Okay? You could do it that way too. But this way we make sure that we start and stop at the right spot.
Yeah, but you know it's
And you know the slope is 5 over 20 or 0.25 or 1.4. Those all represent the slope of the graph, which is our next question. It says explain the meaning of the rate of change and how it relates to the graph.
It explains the slope of the graph.
So the slope is the same as
The rate.
the rate of change. And the word that we use for rate of change when we're talking about distance and time is
Change in distance.
speed.
Oh.
Okay? So, C. The rate of change is Sarah's average running speed. Okay, this is a concept that you have to understand as we move forward. The rate of change, when you're talking about distance and time, is speed. Okay, speed is the rate at which you're changing. Changing what? Changing distance relative to time. Okay? If you had a... never mind, we won't go into that. But the rate of change with relation to distance and time is speed. Okay? And the other thing that this represents, if we're just looking at the graph, it is also the of the graph.
It is also the origin.
Slope.
Slope.
Number 8.
In example 2, we are driving our car, and what happens as you drive a car? Undoubtedly, you use fuel. Okay?
Oh, so I can.
Yeah, I got it.
So, we're given a graph, and it shows the volume of gasoline remaining in a car's tank. Now, you don't have your line drawn. I'm going to give you the coordinates to help you draw your line. You're going to start up here at 0.65. Okay, so it's right on the y-axis. And you're going to draw another dot down here at 500, 5. And then you're going to use a ruler to draw a straight line through those points. Okay. So we are told exactly what the fuel consumption looks like. I'll just draw my axes quick. Okay. And now we need to do a few calculations. We need to do we need to calculate the slope of the graph. Well, what's slope again?
Speed.
Okay, it's related to speed. In this case, we're not...
Consumption.
Hold on. It's only related to speed if you're talking about distance and time. We're not talking about speed here.
Change
So
of
now
rate.
it's run over, rise over run.
It's rise over run when we're talking about a graph. And if you wanted to think about it kind of pictorially, let's say here's the car's fuel tank. We're going from this, pretty close to empty actually, down to about that. And we're finding the rate at which this happens.
I love the smell of gas.
Okay, there's our tank of gas. Make sense? So, we're finding slope.
6 over 5. No, rise
Right.
6 and then run is 5.
Are you sure?
Be careful.
How do you calculate the slope?
So is it practical to use the squares on the grid in this case? Not really, okay? Because the rate on the axes isn't the same. Does that make sense? One is going up by tens and one is going up by hundreds. So it's a bit tough just to count the spaces on the grid. So what you can actually do is you can calculate it based on the coordinates that you have, okay? We can determine the rise and run by looking at the coordinates of our endpoints. This is going to be true in any graph, in any situation. If you have two endpoints, you really don't even need the line in between. You don't even need grid lines. You just need the coordinates. Can anyone make sense of that? Okay, let's talk about this. So we know that the rate of change is the slope of the graph. Right? We've said that in both our examples and in our notes. The rate of change is the slope of the graph. So if you're asked to determine the rate of change, or how long or what rate the gas tank is emptying here, we know we're looking for rise over run. Okay? Now, on a graph, I don't have my grid marks drawn, so I'm not going to count squares, and you're not either, because the rate at which they're growing, the scale is different for the x-axis and the y-axis, or the volume axis and the distance axis. But anyway, we can get this from the points because we know the rise is going to be equal to the change in y. So we're going in y, we're going from here at 5 to here at 65. So this length is our rise. Well, how do I find out how long this stick is that I just drew? If we want to find the change, we want to start with the second coordinate and subtract, okay? Because we're finding the difference. So we're actually starting with 5,
Question, why'd you put
and we're
why was it
subtracting 65, okay? So this is the change in y. This is the rise. The rise is the change, so we start with the new one. We go 5 minus 65.
Why is there
Now,
5? Oh, never mind.
that's going to give us a negative number.
Are those both
Why is that
rises?
important?
Oh, I know.
Because we're going down.
Because it's a negative slope,
Right.
okay? The amount in the tank is going down, so it's a negative slope. Now look at the run. The run is going to go from 0 to what?
500.
To 500. Okay? So, how do we figure that out? Well, 500 minus 0. Five minus 65 is negative 60. 500 minus 0 is 500. We can go ahead and put that in our calculator. You can reduce it if you want to, or you can just punch in your calculator and make sure you have a negative.
0.12.
0.12. Good. So now we need to interpret that. What does that 0.12 negative 12 hundredths, what does that mean?
The rate of change, the slope.
It would probably help if you guys had on your
lose this much gas.
Good. And so distance here is measured in kilometers, and the volume of gas is measured in liters.
Wait, are we? Yeah,
Okay.
I believe you're right.
Volume of gas was measured in liters. So this means for every kilometer driven, the car uses 0.12 liters of fuel.
Is that good or bad?
So the rate of change of the volume of fuel is, and the rate of change, remember it relates two of the variables together, so it's negative 0.12 liters per kilometer.
Is this like real life or is this just like
Can we look at the
or
average
is this like what
of
actually
normal
is?
cars? What's the average?
This is
Okay, lost.
this is would be a bigger vehicle, like a gas guzzler. Okay, does this make sense to you guys?
Yeah.
Kind of.
So what we found out is that it relates to the two variables to each other. We're losing this many liters per kilometer. Just like with speed, we were traveling this distance in this much time. Okay? Yes, Jaden.
So for every, why can't you just say the rate of change for every kilometer driven is 0.2 or 0.1 instead of all that?
The rate of change is negative 0.12
Yeah, but
liters
why'd
per
you write all
kilometer.
the extra stuff? Because that to me, I didn't understand it.
This line?
Yeah.
This line just explains what's really happening here. This is what it means, that the car uses this much fuel for every kilometer. It's the same thing we wrote here. Okay, a little bit more clarification on what it means to have a change in the run and a change in the rise. So let's say I'm gonna do it with a graph, even though you don't need the graph to do it. But let's say we're here at A, okay? And if you have some space somewhere, you can draw this problem. It won't take up too much space. Let's say we're at A, and we're gonna go to B. Okay, A is at 2, 1. And B is at 8, 4. Okay? We know that the slope, the question is, here's A, here's B, you have their coordinates, find the slope. Slope is rise over run. Okay? The rise is going to be the change in the y value. Okay? The run is going to be the change in x. Does that make sense? So that's what I'm saying, is that the rise is going to be the vertical distance between A and B. Between a y value of 1 and a y value of 4.
Y is the up and down.
Okay.
Or yes. Yes.
Why
The-
is the run and the rise?
The run is going to be the change in x. It's the distance between 8 and 2. Okay? So you can already see that my run is going to be 6, right? The distance between 8 and 2. And you can see that my rise is going to be 3, the distance between 4 and 1. So I'm just going to, before getting into that, I'm going to give you another way of saying this. The change in, or the difference in, is represented by this symbol, delta y. You'll learn that a little bit later.
Oh, yeah.
But delta y over delta x means the change in y over the change in x. So slope is the change in y over the change in x. Okay? Yeah, it's just a triangle. It's the Greek letter delta.
Well, that's cool.
Okay?
Why, so that, is that White Delta Hotel uses a triangle?
There you go.
Are you serious?
Okay?
You're joking.
No, not
You
joking.
just
Okay.
pull it from
Delta
that
Hotel.
thing.
Ready? So now look at this, guys.
Delta show.
Please pay attention. Hey. hey. The change in y is the difference in my y values. So watch what I actually do. I'm going to take, and this is going to confuse you a little bit before I explain it. I'm going to take the second y coordinate and subtract the first y coordinate.
Okay.
Okay?
That's not true.
So
That's
4
not
and
bad.
1.
And now in the x's, in the denominator, I'm going to take the second x coordinate
Why
and
do you take the second
subtract
one first?
the first x coordinate.
Because it's
Now,
more.
pay attention. It does not actually matter if you take the first one first or the second one first, as long as you do the exact same thing for the x as you did for the y.
What is
Okay,
subtraction?
so
What do you
watch
put in
this.
the answer, no?
I'm gonna just keep rewriting stuff, and it'll catch on more and more as I'm doing it.
Subtraction is not inverse, right?
What does it
Is that not?
Okay,
It's switching.
so guys, keep going here. So we're talking about the rise. I'm keeping it blue. What we're doing here is we're going to take the y coordinate of the B point and subtract the y coordinate of my A point. Okay? And as if I do it from B to A in the numerator, I have to do it from B to A in the denominator. So in the denominator, I'm going to take the x coordinate of my B point and subtract the x coordinate of my A point.
Didn't we just do this?
To help us, Mr. V.
This is like method
understand
two.
the different
This is,
answers.
guys, this is method 2.
Okay? Here we go. So now I have the y coordinate of B, which is 4, minus the y coordinate of A, which is 1 in the numerator. And in the denominator, I have the x coordinate of B, which is 8, minus the x coordinate of A, which is 2,
Equals 3 over 6.
equals 3 over 6.
Mr. V.
Okay, which equals, yes, you can reduce this to 1/2, or you can call it 0.5.
Yo, Mr. V.
Okay, so now the slope is what we started with. The slope from A to B is positive 0.5 or positive 1/2. Now, if you understand all that, you can go straight from here to here.
Why don't we just do that?
Okay?
Yo, Mr. V.
Okay, there was a really good question, so I'm going to do it again. They said, what if I swapped the B and the A? As long as I do it to the top and the bottom, it will be okay. As long as I keep... So in this case, point B was the second point and point A was the first point. Now basically what I'm saying is, okay, point A is the second point and point B is the first point.
Wait, what?
But as long as I'm consistent, it doesn't make a sweet bit of difference. The math becomes a little bit more difficult, but watch what happens. So the y coordinate of A is 1. The y coordinate of B is 4. So I have 1 minus 4. The x coordinate of A is 2. And the x coordinate of B is 8. I have 2 minus 8. This is negative. 1 minus 4 is negative 3. 2 minus 8 is negative 6,
You can't have 2 negatives, then they cancel out.
which equals 1/2 or 0.5. Exact same answer. So it does not matter which point you consider point 1 or point 2, as long as you're consistent in the numerator and in the denominator. So the question was asked, what if point A or point B is on the other side of one of the axes? What if it's a negative number in one of the coordinates? The exact same rules apply, okay? The change in y over the change in x means that I'm going to take the y coordinate of B and subtract the y coordinate of A. And in the denominator, in the denominator, we're going to take the x coordinate of the B, point B, and subtract the x coordinate of point A. See how I'm being consistent? My A's are on this side, my B's are on this side. Okay, here we go. Plug in what I know. The y coordinate of B is 5, and the y coordinate of A is 1. So I have 5 minus 1. Now in the denominator, my x coordinate gets a little bit sticky here. We've got an x coordinate for B of 4, and minus
and
Negative
negative 2. Okay, so the difference, the vertical difference from here to here is 5 minus 1, that's 4. Okay? But the horizontal distance is actually this 4 plus this 2. Okay? 4 minus negative 2 is actually 4 plus 2, which is 6. I can reduce that to 2/3
Do we have a question?
or 0.66.
Really like integrals.
Yep, pause. This again, guys, this is just the math that you did in units 1 and 2 using integers and positive and negative addition and subtraction. Okay, so you just have to follow the rules that you know. Again, guys, pay attention. A quick demonstration as to what happens if I switch my points. If I call, here I called point B point 2 and point A point 1. What if I swap those? What if I say I take the y coordinate of A minus the y coordinate of B? I can do that as long as, oh boy, this is not good. I can do that as long as I'm consistent in my denominator in taking the x coordinate of A minus the x coordinate of B. Okay, and watch what happens. The y coordinate of A is 1. The y coordinate of B is 5. The x coordinate of A is negative 2. And the x coordinate of B is 4.
It's the same thing.
Negative 4 over negative 6, which equals positive 2 over 3, or 0.6.
So basically, one way takes you to negative, and then the other way just takes you both positive.
Yeah, but if the line, like these lines, this line has a positive slope.
Yeah.
If it had a negative slope, you might find that this way is easier. But you typically, guys, get in the habit of, I'm just showing you that it won't make a difference, but get in the habit of y2 minus y1 over x2 minus x1. That's what's key. Okay, key concepts for lesson 5.4, slope as a rate of change. Pay attention, see if you can get the blanks. Rate of change is the change of one quantity.
Divided.
Related.
No.
Relate. Yeah, relative.
Technically, it
Relative.
is divided by the other, right, Mr.
No.
Yes.
Yep, that's what happens. Yep. But it's relative to the change in another. Okay? Guys, a rate of change requires such as kilometers per hour. Units.
Measurement.
Okay? So if I just wrote this as my answer to the previous question for the fuel, that doesn't make any sense. Okay? It doesn't tell you anything. You have to tell me that you're relating liters to kilometers. You need to have a rate there, okay? Units, such as kilometers per hour. Good. When a relationship is graphed, the
slope.
Yeah.
No, not the slope.
Yeah.
No.
The slope.
You just said.
The slope. The slope.
Right.
Good. Last one. To find the slope of a line segment that joins 2 points, this is what we described, subtract the y values to get the rise, and subtract the x values to get the run. The practice problems are on the bottom. They come from page 522, numbers 4 through 13, and the worksheet that you find on page 18 in your notebook.
Enjoy! Can we start?